Picture this: a universe so young, so raw, it hasn't even figured out how to make starlight yet. No galaxies, no planets, just an endless sea of darkness. But somewhere in that void, the very first stars were born. Not the ones we know today, though. These were monsters, dark stars, cosmic giants fueled not by fire, but by something far stranger: dark matter. And here's the wildest part: we've never seen one, not a single glimpse. They should be out there, lurking in the shadows of the early cosmos, but they've stayed hidden for over 13 billion years. So what's going on? Why can't we find them? Are we missing something? Or is the universe playing the ultimate game of hide and seek? Stick around, because by the end of this video, you'll understand why dark stars are the biggest cosmic mystery no one's talking about, and how we might finally be on the verge of uncovering them. This isn't just astronomy, it's a detective story written in the fabric of space itself, and you're about to get front row seats to the hunt. Now, let's rewind the cosmic clock way back to the very beginning. Imagine a universe that's less than a second old. It's not the star-studded expanse we know today. Instead, it's a seething, chaotic soup of particles, hotter than the core of any star. This is the aftermath of the Big Bang, where space itself is stretching at a mind-bending pace, and matter is so densely packed that light can't even travel freely. In these first moments, the universe was a playground for the simplest ingredients: hydrogen, helium, and a mysterious, invisible guest: dark matter. There were no heavy elements like carbon or oxygen, no planets, no galaxies. Just a fog of primordial gas simmering in the darkness. But here's the twist: dark matter wasn't just a passive spectator. It was the unseen architect shaping everything. Unlike ordinary matter, dark matter doesn't interact with light or other particles the way atoms do. It doesn't collide, doesn't emit radiation. It just clumps together under gravity, forming vast, invisible scaffolds. And in those early times, these dark matter structures became the gravitational anchors for the first stars. Think of them as cosmic seeds pulling in the surrounding gas, compressing it into dense knots. Without dark matter's grip, the universe might have stayed a featureless void forever. But here's where things get truly fascinating. The lack of heavy elements meant the gas in the early universe was pristine, free of the dust and metals that help modern stars cool and collapse efficiently. So when these first clouds of hydrogen and helium got squeezed by dark matter's pull, they didn't fragment into small stars like we see today. Instead, they grew and grew and grew. We're talking about behemoths, stars with masses millions of times greater than our Sun, and their power source, not nuclear fusion alone, but dark matter annihilation, a process where dark matter particles collide and release vast amounts of energy. This was the perfect storm for dark stars to emerge, a universe dominated by dark matter, filled with simple, pure gas, and lacking the heavy elements that would later dictate how stars form. It was a recipe for something the cosmos would never see again. And yet, despite their colossal size and significance, these dark stars remain hidden, their glow lost in the depths of time. But why? Well, that's a mystery we're just beginning to unravel. Now, let's zoom in on the unsung hero of this cosmic story, dark matter. While ordinary matter gets all the spotlight for forming stars and galaxies, dark matter was the silent force that made the first stars possible. Picture it like this: if the early universe was a construction site, dark matter was the invisible framework holding everything together. Without it, those primordial clouds of gas would have just drifted apart, leaving nothing to ignite the cosmos. Here's how it worked. Dark matter's gravity acted like a cosmic glue, pulling hydrogen and helium into dense pockets. But unlike ordinary matter, which can collide, heat up, and radiate energy away, dark matter particles pass right through each other. This meant dark matter could clump together faster and more efficiently, creating massive structures long before regular matter could catch up. These dark matter halos, as scientists call them, became the gravitational anchors for the first stars. Think of them as the scaffolding for a skyscraper, invisible but essential for stability. Now, here's the twist that made dark stars possible. In those early halos, dark matter didn't just sit there, it annihilated. When two dark matter particles collided, they could destroy each other, releasing a burst of energy. This process wasn't like the nuclear fusion powering modern stars. Fusion requires extreme heat and pressure to squeeze atoms together, but dark matter annihilation could happen at much lower temperatures. So while ordinary stars rely on fusion in their cores, dark stars had this extra energy source woven throughout their entire structure, like a star with its furnace spread evenly from core to surface. This dual energy mechanism let dark stars grow to staggering sizes. A modern star like our Sun balances gravity's pull with the outward pressure from fusion, keeping it relatively compact. But a dark star, fueled by dark matter annihilation, could keep accumulating gas without the same limits. Estimates suggest some might have reached masses millions of times greater than the Sun, dwarfing even the largest stars we see today. Yet dark matter's role wasn't just about size, it also shaped these stars' lifespan. In a normal star, when fusion fuel runs out, the star collapses or explodes. But dark stars could theoretically keep burning as long as dark matter kept flowing into them. Some models suggest they might have lived for millions of years, far longer than the first generation of fusion-powered stars. And when their dark matter fuel finally ran out, they likely collapsed into supermassive black holes, seeding the centers of galaxies we see today. This interplay between dark matter and ordinary gas was a delicate dance. Too much dark matter and the star's energy output would blow the gas away. Too little, and the gas wouldn't stay hot enough to resist collapsing into smaller fragments. It took just the right conditions that only existed in the universe's infancy. That's why dark stars are such a unique chapter in cosmic history, and why finding them would rewrite our understanding of how the first structures in the universe took shape. Shifting our gaze from the ancient cosmos to the stars we know today, the differences between dark stars and modern stars are nothing short of astronomical. Imagine holding a candle next to a blazing wildfire. That's the scale we're talking about. While today's stars, like our Sun, are powered by nuclear fusion in their cores, dark stars drew energy from something far more exotic, the annihilation of dark matter. Let's start with size. The Sun, which feels colossal to us, is actually quite average by stellar standards. It's about 109 times wider than Earth and makes up 99.8% of our solar system's mass. But dark stars, they were behemoths. Current models suggest they could have been millions of times more massive than the Sun. To put that in perspective, if our Sun were a grape, a dark star would be the size of a stadium. That sheer bulk came from their unique energy source. While modern stars rely on fusion, squeezing hydrogen atoms into helium under crushing pressure, dark stars had dark matter annihilation woven throughout their entire structure, like a furnace with no off switch. Now let's talk energy. Fusion is a picky process. It requires temperatures of at least 10 million degrees and immense pressure to overcome the repulsion between atomic nuclei. That's why fusion only happens in the cores of modern stars, where conditions are just right. Dark matter annihilation, on the other hand, didn't need such extreme environments. When two dark matter particles collided, they could release energy without the need for heat or pressure. This meant dark stars didn't have a centralized engine like modern stars. Instead, energy production was spread evenly, allowing them to grow without the same physical constraints. This difference in energy sources also affected their lifespans. A star like the Sun will burn for about 10 billion years before running out of hydrogen and swelling into a red giant. Dark stars, fueled by dark matter, could have lasted much longer, perhaps millions of years, as long as dark matter kept flowing into them. And when that fuel ran dry, they didn't fade quietly. Many likely collapsed into supermassive black holes, which might explain why we see these monsters lurking in the centers of galaxies today. But here's the kicker: dark stars wouldn't have looked like the stars we see tonight. Modern stars glow because their hot surfaces emit light across the spectrum, from visible to ultraviolet. Dark stars, though, would have been cooler and fainter, with most of their energy radiating as infrared. If you could somehow stand near one, it might appear as a dim, eerie red orb, nothing like the brilliant points of light we're used to. This contrast isn't just academic. Understanding dark stars helps explain why the early universe evolved the way it did. They might have been the seeds for the first galaxies, the architects of cosmic structure. And that's why finding them, or proving they existed, isn't just about rewriting stellar physics. It's about uncovering the hidden blueprint of the universe itself. Now, with this cosmic puzzle in mind, let's turn to the brilliant minds who first dared to imagine these invisible giants, because every radical idea starts with a bold theory, and dark stars are no exception. Now, let's peel back the layers of theory that brought dark stars into the realm of scientific possibility. Every cosmic mystery begins with a bold idea, and in the case of dark stars, that spark came from the pioneering work of astrophysicists Katherine Freese and Paolo Gondolo. Their research didn't just tweak existing stellar models, it upended them, proposing a radical new way to think about the universe's first stars. At the heart of their theory is a simple but profound shift. Dark matter isn't just an invisible scaffolding for galaxies. It could have been the fuel for stars themselves. Traditional stellar formation hinges on gravity pulling together gas and dust until nuclear fusion ignites. But Freese and Gondolo asked, what if dark matter's unique properties, its ability to interact gravitationally but barely otherwise, could power stars in a completely different way? Their models showed that in the early universe, where dark matter was densely packed, these particles could collide and annihilate, releasing enough energy to heat and sustain a star without fusion ever occurring. Breaking down the physics, their work revealed something extraordinary. While ordinary stars rely on the intense pressure and temperature at their cores to fuse atoms, dark stars would operate like cosmic slow cookers. Dark matter annihilation would gently warm the star's interior, creating a stable, long-lasting energy source. This process wouldn't concentrate in a core but would permeate the entire star, allowing it to grow to staggering sizes without collapsing under its own weight. The implications of this challenged traditional astrophysics. For decades, stellar formation was neatly explained by fusion-powered models. But Freese and Gondolo's work forced scientists to reconsider, could the first stars have followed a different recipe? Their calculations suggested yes, and with startling consequences. If dark stars existed, they'd rewrite the timeline of cosmic dawn, potentially delaying the emergence of fusion-powered stars and altering how the first heavy elements were forged. Skeptics, of course, raised eyebrows. Without direct evidence, dark stars remained a tantalizing what if. But Freese and Gondolo's models held up to scrutiny, offering testable predictions. For instance, dark stars would leave behind distinct chemical signatures or seed supermassive black holes, clues that later missions like the James Webb Space Telescope could hunt for. What makes their theory so compelling isn't just its audacity but its elegance. It ties together two of cosmology's biggest puzzles, the nature of dark matter and the origins of cosmic structure. If dark stars existed, they'd be the missing link between the formless early universe and the galaxies we see today. As we piece together this cosmic detective story, the next question is obvious. If dark stars were real, why haven't we spotted them yet? The answer lies in the very tricks they use to hide a challenge that brings us to the cutting edge of modern astronomy. Now, let's turn our attention to the lifespan of these cosmic giants, because dark stars didn't just burn bright and fast. Unlike modern stars that race through their fuel in a blaze of fusion, dark stars operated on a different clock. Picture a star not powered by the frantic rush of nuclear reactions, but by the steady, relentless annihilation of dark matter. This unusual energy source gave them an almost unthinkable longevity, lasting not thousands but potentially millions of years. Here's why that matters. In the early universe, where dark matter was dense and abundant, these stars could have grown to monstrous sizes without the usual constraints. While a star like our Sun fuses hydrogen in its core until it runs out and eventually dies in a relatively short cosmic timespan, dark stars had a built-in advantage. Their energy came from dark matter particles colliding and annihilating throughout their vast bodies, not just in a central core. This meant they could maintain equilibrium for eons, glowing faintly but persistently in the primordial darkness. But nothing lasts forever, not even dark stars. Their fate hinged on the availability of dark matter. Think of it like a campfire. A regular star is like a pile of dry wood. It burns hot and fast. A dark star, though, is more like a peat fire, slow burning and steady. As long as there's fuel, it keeps going, but what happens when the fuel runs out? One possibility is collapse. If a dark star's dark matter supply dwindled, gravity would finally take over. Without that internal energy source to counteract its immense weight, the star could shrink and compress, potentially forming one of the universe's first supermassive black holes. This would explain a long-standing cosmic mystery: how supermassive black holes appeared so early in the universe's timeline. Dark stars might have been their nurseries. Alternatively, some models suggest dark stars could have simply faded away. As dark matter became less concentrated over time, annihilation would slow, causing the star to cool and gradually dissipate. Instead of a dramatic collapse, these cosmic behemoths might have dimmed into obscurity, dissolving back into the fabric of space. What's fascinating is the ripple effect of either scenario. If dark stars collapsed into black holes, they could have jump-started the growth of galaxies. If they faded quietly, they might have left behind vast, empty regions in the early cosmos. Either way, their lifespan wasn't just a footnote, it shaped the universe we see today. And that leads us to the next piece of the puzzle. If dark stars were so long-lived and influential, where's the evidence they existed at all? The answer lies in the cosmic shadows they left behind, clues hidden in the light of the earliest galaxies. But that's a story for another moment. Now, let's step back into the cosmic dark ages, that mysterious stretch of time before the first starlight pierced the universe. This era wasn't just empty blackness. It was a silent battleground where the fate of the cosmos was being decided, and dark stars might have played a hidden but crucial role. Imagine the universe as a newborn, still cooling from the heat of the Big Bang. For hundreds of millions of years, it was filled with a fog of hydrogen gas, so thick that light couldn't travel through it. This was the cosmic dark ages, a period before stars as we know them existed. But here's where dark stars changed the story. While most of the universe was shrouded in darkness, these primordial giants could have been the first faint sources of light, glowing not from fusion but from dark matter annihilation. Their dim, steady radiance might have been the first whisper of illumination in an otherwise pitch-black cosmos. This faint glow could have had a domino effect on one of the universe's most critical transitions, reionization. As the first stars and galaxies later ignited, their ultraviolet light began to break apart the hydrogen fog, ionizing it and clearing the way for light to travel freely. But dark stars may have gotten a head start. Their unique light, though weak, could have begun the process of chipping away at that hydrogen barrier, subtly preparing the universe for the flood of starlight to come. Think of it like a pre-dawn glow softening the darkness before sunrise. The implications are staggering. If dark stars contributed to reionization, they didn't just exist, they helped shape the very structure of the universe. By ionizing pockets of hydrogen early on, they might have influenced where and how the first galaxies formed. It's possible that the regions around dark stars became the seeds for future cosmic structures, like invisible architects laying the groundwork for everything that followed. But there's a twist. Dark stars didn't emit light the way modern stars do. Their energy came from a completely different process, which means their light would have had a unique signature, one that's incredibly hard to detect across billions of years. That's why linking them to reionization is such a challenge. The evidence is buried in the faintest whispers of ancient light, waiting for telescopes like the James Webb to decode it. So, what does this mean for our understanding of the cosmic dark ages? It suggests this era wasn't just a blank slate. Dark stars could have been the unsung pioneers, quietly shaping the universe long before the first galaxies took center stage. Their story isn't just about what they were, it's about how they set the scene for everything that came after. And that brings us to the next chapter, the cutting-edge tools we're using to hunt for their elusive traces. Now, let's tackle the million-dollar question. Why haven't we spotted these cosmic giants yet? The hunt for dark stars isn't just a needle in a haystack scenario. It's like searching for a flickering candle hidden behind a mountain of fog, billions of light years away. The challenges are as immense as the stars themselves, and they reveal just how much the universe loves playing hide and seek. First, consider the light, or rather, the lack of it. Dark stars don't shine like the stars we see today. Modern stars are powerhouses of nuclear fusion, blasting out intense light across the spectrum. But dark stars, their glow comes from dark matter annihilation, a process that produces a faint, steady trickle of energy. Imagine comparing a roaring bonfire to the soft embers of a dying campfire. That's the difference we're dealing with. Their light isn't just dim, it's drowned out by the glare of younger, brighter stars and galaxies that formed later in cosmic history. Then there's the distance problem. Dark stars existed in the universe's infancy, meaning their light has been traveling for over 13 billion years to reach us. Over that mind-bending stretch of time, the expansion of the universe has stretched their light into the infrared spectrum, a wavelength range that's notoriously difficult to observe. It's like trying to read a faded, ancient manuscript where half the ink has vanished. Even worse, the early universe was filled with that thick hydrogen fog we talked about earlier, scattering and absorbing what little light these stars emitted. By the time their photons reach us, they're whispers in a cosmic storm. Modern telescopes face another hurdle: resolution. Even our most advanced instruments, like the Hubble Space Telescope, struggle to pick out individual objects from this era. The early universe was a crowded place, with stars and proto-galaxies clustered close together. Spotting a dark star in that chaos is like trying to distinguish one grain of sand on a beach from orbit. And let's not forget contamination. Light from closer, brighter objects often obscures the faint signals we're desperate to detect. It's cosmic noise pollution at its most frustrating. But here's the kicker: dark stars might not even look like stars in the traditional sense. Without the violent processes of fusion, they could have been bloated, diffuse monsters, spanning millions of times the sun's volume but glowing with the warmth of a space heater. Their structure alone defies what modern telescopes are designed to find. We're essentially searching for something that breaks every rule we've learned about stellar detection. So where does that leave us? It's not just a technical challenge, it's a paradigm shift. To find dark stars, we need to rethink what a star even is. That's why tools like the James Webb Space Telescope are game changers. Its infrared eyes and unprecedented sensitivity are tailor-made for this hunt. But even with these advancements, the search is a marathon, not a sprint. Every flicker of ancient light could be a clue or another dead end, and that's what makes this one of the most thrilling puzzles in modern astrophysics. Here's how the next section would unfold, naturally continuing from the previous segment. Now, here's where the story takes a thrilling turn. Enter the James Webb Space Telescope, humanity's most ambitious eye on the cosmos. Unlike its predecessors, Webb isn't just another telescope, it's a time machine designed to pierce through the universe's earliest shadows. With its gold-coated mirrors and blistering sensitivity to infrared light, Webb is the first instrument capable of spotting the faint, stretched glow of dark stars hiding in the cosmic dawn. What makes Webb so special? It all comes down to infrared. Remember how the expansion of the universe shifts ancient starlight into longer, redder wavelengths. Webb's instruments are fine-tuned to catch exactly that. While Hubble struggled to see past the veil of cosmic dust, Webb's infrared vision cuts through it like a hot knife through butter. It's the difference between squinting through frosted glass and stepping into a crystal-clear observatory. And for dark stars, that clarity is everything. Their lukewarm glow, emitted at infrared wavelengths, finally has a detector powerful enough to pick it up. But Webb's power isn't just about sensitivity, it's about precision. Early universe objects are often smudged into blobs by lesser telescopes, but Webb's resolution can isolate individual structures from 13 billion years ago. Imagine trying to read a street sign from a mile away with blurry binoculars versus a high-powered lens. That's the leap Webb provides. For the first time, we might distinguish a solitary dark star from the haze of primordial galaxies, or even catch clusters of them lighting up the cosmic dark ages like ghostly beacons. There's another ace up Webb's sleeve, its spectrographs. These tools don't just detect light, they dissect it, revealing the chemical fingerprints of whatever they observe. If dark stars exist, their spectra would lack the telltale signatures of heavy elements forged in fusion, instead showing the unique markers of dark matter annihilation. It's like identifying a suspect not by their face but by a distinct shadow they cast. One match to these theoretical profiles and the hunt could be over. Of course, challenges remain. Webb's data is complex, and dark stars, if they're out there, won't wave hello. Astronomers are combing through early snapshots, searching for anomalies, objects too large, too dim, or too oddly colored to fit conventional models. Some candidates, like those bizarrely bright early galaxies, are already raising eyebrows. Could they actually be dark stars in disguise? The next few years of observations might crack the case. Webb's mission isn't just about finding dark stars, it's about rewriting cosmic history. If these giants exist, they'd bridge the gap between the Big Bang's simplicity and the universe we see today. And if they don't, well, that's a mystery in itself. Either way, every pixel Webb beams back brings us closer to answers. The universe's first stars might finally step into the light, and we've got the best seat in the house to watch it happen. Now, let's turn our attention to the real excitement, those puzzling glimmers in the data that might just be our first glimpse of dark stars. Recent observations from the James Webb Space Telescope have spotted something unexpected in the early universe, galaxies that shine far brighter than anyone predicted. These aren't just ordinary galaxies, they're colossal, dazzling, and oddly young, appearing barely a few 100 million years after the Big Bang. The question on everyone's mind. Could these be dark stars in disguise, or even clusters of them lighting up the cosmic stage? What makes these objects so suspicious? For starters, their sheer brightness defies conventional models. Normal galaxies from this era shouldn't be this luminous, not unless they're packed with stars forming at impossible rates. But what if the light isn't coming from billions of tiny stars, but from a handful of monstrous dark stars instead? Picture this, a single dark star, millions of times heavier than our Sun, glowing steadily from dark matter annihilation. A few of these titans could outshine an entire galaxy of ordinary stars while remaining almost invisible in other wavelengths. Then there's the matter of their size and temperature. Some of these candidate objects are too warm to be typical early galaxies, but too cool for the supermassive black holes we're used to seeing. That's a sweet spot right where dark stars should sit, lukewarm giants radiating infrared light, just as theories predicted. Even their locations line up. They're found in dense regions of the early universe, exactly where dark matter would have been plentiful enough to fuel them. But here's where the debate gets heated. Skeptics argue these bright objects could still be something else, perhaps hyperactive star-forming galaxies or even early quasars with unusual properties. Without a smoking gun, like a definitive spectral signature of dark matter annihilation, the mystery remains. That's why astronomers are racing to analyze Webb's latest data, searching for tiny clues in the light's composition. A single mismatch in the expected chemical fingerprints could tilt the scales. The implications are staggering. If these candidates turn out to be dark stars, it would confirm a radical new chapter in stellar evolution, one where dark matter, not just gas, shaped the universe's first light. And if they're not, well, their very existence still forces us to rethink how galaxies formed in the cosmos' infancy. Either way, Webb's discoveries are stirring the pot, proving that the early universe was far stranger and more vibrant than we ever imagined. The hunt isn't just about finding dark stars anymore, it's about unraveling the rules of cosmic dawn itself. But let's take this one step further. What if dark stars didn't just fade away? What if their fate was far more dramatic, shaping the cosmos in ways we're only beginning to understand? Here's where the story takes a twist. Some scientists believe these primordial giants didn't just burn out quietly. Instead, they may have collapsed under their own immense gravity, becoming the universe's first supermassive black holes. Think about it. A dark star, bloated to millions of times the mass of our Sun, would have had a staggering gravitational pull. As it consumed the last traces of dark matter fueling it, the star's core could have imploded, triggering a catastrophic collapse. No fiery supernova, no messy explosion, just a silent, crushing descent into darkness. The result, a black hole of unimaginable size lurking in the depths of the early universe. This isn't just speculation. It could solve one of astronomy's biggest puzzles: how supermassive black holes appeared so quickly after the Big Bang. Take the quasars we've spotted in the infant universe lighthouses of radiation powered by black holes billions of times heavier than the Sun. By conventional models, there simply wasn't enough time for these monsters to grow from smaller black holes. But if they started as dark stars, their head start makes perfect sense. The connection goes even deeper. Look at the galaxies we see today. Nearly everyone, including our own Milky Way, hosts a supermassive black hole at its core. Their origins have long been murky, but dark stars offer a compelling origin story. Imagine a young galaxy forming in a dense cloud of dark matter, its center anchored by a collapsing dark star. Over eons, that black hole could have grown, swallowing gas and stars while shaping the galaxy around it. Of course, not everyone's convinced. Critics point out that we've never directly observed a dark star's collapse, and alternative theories exist. Maybe supermassive black holes grew from dense star clusters, or perhaps they formed through exotic physics we haven't uncovered yet. But here's the thing. Dark stars fit the evidence we have, from the timing of early quasars to the eerie glow of Webb's candidate objects. Whether this hypothesis holds up or not, it forces us to rethink the cosmic rulebook. Dark stars aren't just relics of the past. They could be the missing link in our understanding of black holes, galaxies, and the universe's most powerful engines. And as Webb peers deeper into the cosmos, we might finally find the proof we've been searching for, or uncover something even stranger. Now, let's peel back the layers of what made dark stars so extraordinary, their power source. Unlike the stars we see today, which shine by fusing atoms in their cores, dark stars ran on something far more mysterious: dark matter annihilation. Picture this as the ultimate cosmic fuel, one that doesn't burn like hydrogen but instead vanishes in bursts of pure energy. Here's how it works. Dark matter, that invisible substance making up most of the universe's mass, isn't just sitting idle. According to leading theories, certain types of dark matter particles could be their own opposites. When two of these particles collide, they annihilate each other, converting their mass directly into energy. No ash, no residue, just a clean, efficient release of power. Inside a dark star, this process would have been constant. Imagine a vast, swirling core where dark matter particles collide like frenzied fireflies, each collision releasing energy that heats the star from within. Unlike fusion, which requires extreme temperatures and pressures to squeeze atoms together, dark matter annihilation could happen at much lower energies. That means a dark star wouldn't need a dense, blazing core like our Sun. Instead, it could be diffuse and cool, yet still radiant, glowing softly from the energy of these particle collisions. The numbers are staggering. A single dark star, fed by the dense dark matter halos of the early universe, could have produced energy equivalent to millions of modern stars without a single nuclear reaction. This isn't just a tweak to how stars work, it's a complete rewrite. Fusion is a delicate balancing act, but dark matter annihilation is relentless. As long as dark matter kept flowing into the star, it would keep shining, potentially for millions of years. But here's the twist. Unlike fusion, which leaves behind heavier elements, dark matter annihilation leaves no trace. That's why dark stars wouldn't have enriched the cosmos with metals as modern stars do. Their light came from something invisible, and when they faded or collapsed, they took their secrets with them. To grasp just how strange this is, compare it to a campfire. A normal star is like burning logs. They produce heat and light, but also smoke and ash. A dark star, it's like a flame fueled by ghostly kindling that vanishes without a trace. No wonder these objects are so hard to find, yet this very strangeness might be our best clue. If dark stars glowed differently, cooler, larger, and without the chemical fingerprints of fusion, then telescopes like Webb could spot their faint, unusual light. And if they did, it wouldn't just confirm dark stars, it would prove that dark matter can annihilate, opening a window into one of physics' greatest unsolved mysteries. The hunt isn't just about ancient stars, it's about uncovering the hidden rules of the universe itself. Now, let's step back and consider another possibility. While dark stars are a fascinating idea, they aren't the only explanation for the mysteries of the early universe. Some scientists argue that what we're seeing could instead be the work of another kind of cosmic pioneer, population 3 stars. These are the first generation of stars born from pure hydrogen and helium without a trace of heavier elements. They were massive, hot, and short-lived, burning fiercely before exploding as supernova. So, how do population 3 stars differ from dark stars? For one, they rely on fusion, just like modern stars, but with a key twist. Without elements like carbon or oxygen to help cool their cores, they could grow to incredible sizes, some reaching hundreds of times the mass of our Sun. Their intense ultraviolet light would have played a crucial role in ionizing the early universe, a process we know happened but still struggle to fully explain. But here's where the debate heats up. Population 3 stars, while powerful, don't account for one big puzzle: the sheer brightness of some early galaxies spotted by telescopes like Webb. If these galaxies were filled with ordinary stars, even massive ones, their light shouldn't be as intense as what we're observing. That's where dark stars come back into the picture. Their unique energy source, dark matter annihilation, could produce far more light over much longer timescales, potentially explaining those unusually luminous early galaxies. Of course, not everyone is convinced. Skeptics point out that we've never directly detected dark matter, let alone seen it annihilate. Without concrete proof, dark stars remain a tantalizing but unproven hypothesis. On the other hand, population 3 stars fit neatly into our understanding of stellar physics, even if they can't explain every anomaly. Yet the absence of evidence isn't evidence of absence. Just because we haven't found dark stars yet doesn't mean they aren't out there. The early universe was a vastly different place, and our models are still catching up to its complexities. Whether the truth lies with dark stars, population 3 stars, or some combination of both, one thing is clear: the first stars hold the key to understanding how our cosmos evolved from darkness to light. As we peer deeper into the past, each new discovery brings us closer to solving this cosmic whodunit. The answer, whatever it may be, will rewrite the story of how our universe lit up for the very first time. Now, let's take a closer look at how scientists are piecing together the puzzle of dark stars, not with telescopes, but with the power of supercomputers. These machines allow researchers to recreate the extreme conditions of the early universe, testing whether dark stars could have formed and how they might have behaved. Imagine feeding all the known physics of dark matter, gravity, and primordial gas into a digital universe and hitting play. That's essentially what these simulations do, offering us a front-row seat to the birth of cosmic giants we've never seen. One of the most fascinating revelations from these simulations is just how differently dark stars grow compared to ordinary stars. While modern stars like our Sun form when dense clouds of gas collapse under their own gravity, dark stars rely on the constant energy input from dark matter annihilation. Supercomputers show that this process creates stars that balloon to staggering sizes, some reaching millions of times the mass of the Sun without ever igniting nuclear fusion in their cores. Instead, they glow faintly, powered by the slow burn of dark matter particles colliding and releasing energy. The visualizations from these simulations are nothing short of breathtaking. Picture a vast, swirling vortex of hydrogen and helium, with dark matter's invisible pull shaping the gas into a massive, diffuse structure. Unlike the dense, fiery balls we associate with stars, dark stars appear more like glowing fog banks, their light uneven and shimmering as dark matter annihilation flickers within them. Some models even suggest they could have had irregular, lumpy shapes, their surfaces bubbling with energy as dark matter interactions ebbed and flowed. But simulations aren't just about creating pretty visuals. They're helping scientists tackle real mysteries. For instance, they've shown that dark stars could have lived for millions of years, far longer than the short, violent lives of population 3 stars. This longevity might explain why some early galaxies observed by the James Webb Space Telescope appear so bright. If dark stars lingered in these galaxies, their cumulative light could account for the puzzling intensity we see. Of course, simulations aren't perfect. They rely on our current understanding of dark matter, which is still full of gaps. If dark matter behaves differently than we've assumed, say, if it doesn't annihilate as efficiently, these models would need to be revised. But even with uncertainties, they've given us a crucial tool for exploring a universe we can't yet observe directly. Every new simulation refines our search, telling us where to look and what signatures might betray a dark star's presence. What's next? As supercomputers grow more powerful, so too will our virtual experiments. Future simulations might reveal whether dark stars could have left behind detectable traces, like unique chemical fingerprints in ancient gas clouds. Or perhaps they'll uncover new ways these cosmic anomalies influenced the universe's evolution, shaping everything from the first galaxies to the black holes that anchor them. One thing's certain: the digital universe is our best guidebook to a reality we're only beginning to imagine. Now, let's turn our attention to one of the most intriguing questions about dark stars. Did they leave behind a chemical legacy that shaped the universe as we know it? When we think about the ingredients that make up planets, life, and even ourselves, we're talking about heavy elements like carbon, oxygen, and iron. These elements weren't around in the early universe. They were forged in the hearts of stars. But here's the twist: dark stars don't play by the same rules as ordinary stars, so their role in this cosmic recipe is anything but straightforward. Unlike modern stars, which create heavy elements through nuclear fusion, dark stars are powered by dark matter annihilation. That means they don't generate the extreme temperatures and pressures needed to fuse lighter elements into heavier ones. So at first glance, it might seem like dark stars left no chemical fingerprint behind. But dig a little deeper and the story gets more interesting. Some theories suggest that when dark stars eventually exhausted their dark matter fuel, they could have collapsed under their own gravity. This collapse might have triggered runaway nuclear fusion in their cores, briefly turning them into monstrous versions of ordinary stars. In those final moments, they could have produced bursts of heavy elements, scattering them into space. Alternatively, if dark stars collapsed directly into black holes, the surrounding gas might have been heated to incredible temperatures, creating shock waves that forged new elements. Then there's the question of timing. Dark stars lived far longer than the first generation of regular stars, known as population 3 stars. If they lingered in the early universe, their eventual demise could have overlapped with the birth of later stellar generations. That means the heavy elements they might have produced could have mixed with the raw materials for newer stars and planets, subtly influencing the chemistry of the cosmos. Of course, this is all speculation, but it's speculation with real stakes. If dark stars did contribute heavy elements, their chemical signature might still be detectable in the oldest stars or gas clouds we can observe today. Finding traces of unusually high concentrations of certain elements or patterns that don't match predictions from ordinary stellar nucleosynthesis could be a clue that dark stars once played a role in seeding the universe. The James Webb Space Telescope is already giving us glimpses of ancient galaxies with surprising chemical compositions. Could some of those anomalies be the fingerprints of dark stars? It's a tantalizing possibility, one that reminds us how much we still have to learn about the universe's earliest chapters. Whether or not dark stars left a lasting mark, their story challenges us to rethink how the cosmos built itself from the ground up. And that's a mystery worth chasing. Up next, we'll zoom out to see where dark stars fit into the grand timeline of the universe and how their existence could rewrite our understanding of cosmic evolution. Now, stepping back to see the bigger picture, let's map out where dark stars fit into the universe's grand timeline and why their potential existence could turn cosmic history on its head. Imagine the universe as a storybook, with each chapter marking a pivotal moment in its evolution. The first few pages are dominated by the Big Bang, followed by a murky era known as the Cosmic Dark Ages, where no stars or galaxies existed. This is where dark stars enter the scene, not as a footnote but as potential game changers. If dark stars did form, they'd be among the very first structures to emerge, lighting up the darkness hundreds of millions of years before ordinary stars could ignite. Their sheer size and longevity mean they could have shaped the cosmos in ways we're only beginning to grasp. For instance, their intense gravitational pull might have acted like cosmic anchors, drawing in surrounding gas and dark matter to form the seeds of the first galaxies. Without them, the universe's scaffolding might have looked entirely different, delaying the birth of galaxies as we know them. But here's where the timeline gets even more intriguing. Dark stars could have lived for millions of years, far longer than the short-lived population 3 stars. If they endured long enough, their eventual collapse, whether into black holes or through explosive transformations, might have overlapped with the next phase of cosmic evolution. Picture this: as the first ordinary stars began to flicker to life, dark stars could have been dying, seeding the cosmos with heavy elements or even birthing the first supermassive black holes. That means the universe's transition from darkness to light might not have been a clean break but a messy, interconnected dance. This timeline isn't just academic, it has real consequences for how we understand the universe today. Take supermassive black holes, for example. These behemoths found at the centers of galaxies are puzzlingly large for how early they appear in the cosmic record. If dark stars collapsed into them, it would solve a major mystery, explaining how such massive objects formed so quickly. Similarly, the distribution of galaxies and the patterns of cosmic structure we see today might bear the invisible fingerprints of dark stars' gravitational influence. Of course, the absence of dark stars would be just as revealing. If future observations rule them out entirely, we'd need to rethink how the early universe lit up and how structures emerged from the primordial soup. Either way, dark stars force us to question the textbook narrative of cosmic evolution, reminding us that the universe's history is still being written. As we piece together this timeline, one thing becomes clear: dark stars aren't just relics of the past, they're keys to understanding how the universe grew from a hot, dense speck into the vast, luminous web we see today. And with cutting-edge telescopes like James Webb peeling back the layers of time, we might soon find out just how pivotal their role really was. Up next, we'll look ahead to the future of dark star hunting and the next generation tools that could finally bring these cosmic ghosts into the light. Now, let's turn our gaze to the future, where the next generation of telescopes promises to shine a light on the mysteries of dark stars. While the James Webb Space Telescope has already begun revolutionizing our view of the early universe, it's just the opening act. Upcoming observatories like LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, and the Nancy Grace Roman Space Telescope are set to push the boundaries even further, equipped with technology that could finally settle the debate over dark stars once and for all. LUVOIR, in particular, is a game-changer. Imagine a telescope with a mirror up to 15 meters in diameter, dwarfing even James Webb's impressive 6.5 meters. This colossal light-gathering power means LUVOIR could detect the faintest glimmers of dark stars, peering deeper into the cosmic dawn than ever before. Its advanced ultraviolet and infrared capabilities are tailor-made for spotting these ancient objects, whose light has been stretched into these wavelengths by the expansion of the universe. If dark stars are out there, LUVOIR precision could reveal their telltale signatures, distinguishing them from ordinary stars or distant galaxies. Then there's the Roman Space Telescope, named in honor of NASA's first chief astronomer. While it may not match LUVOIR's sheer size, its wide-field surveys will cover vast swaths of the sky, hunting for anomalies that could point to dark stars. Roman's strength lies in its ability to map the universe in unprecedented detail, identifying regions where dark stars might have clustered. By analyzing the light from these patches, astronomers could uncover subtle clues, like unusual chemical compositions or energy patterns, that betray the presence of dark matter-powered stars. But these telescopes won't just be looking for dark stars directly. They'll also investigate the aftermath of their existence. For instance, if dark stars collapsed into supermassive black holes, Roman and LUVOIR could trace the distribution and growth of these black holes across cosmic time, testing whether they align with predictions from dark star models. Similarly, by studying the earliest galaxies, these observatories might find evidence of dark stars' gravitational influence, perhaps in the way galaxies are clustered or how quickly they formed. Of course, the absence of dark stars would be just as significant. If these next-gen tools come up empty-handed, it would force astronomers to revisit their theories about the early universe's structure and energy sources. Either way, the data will be transformative, narrowing down the possibilities and guiding future research. What makes this era so exciting is that we're no longer limited by technology. With each new observatory, we're peeling back layers of the universe's history, inching closer to answering one of cosmology's biggest questions. The hunt for dark stars is far from over. It's just entering its most thrilling chapter. And as these telescopes come online, we might finally unlock the secrets of the universe's first and strangest stars. Up next, we'll dive into how dark stars have captured the imagination beyond science, inspiring everything from blockbuster films to philosophical debates. Because sometimes the most elusive objects in the cosmos leave the brightest marks on our culture. Now, let's step away from the cutting edge of cosmic research for a moment and explore how dark stars have ignited imaginations beyond the realm of science. These mysterious celestial objects haven't just fascinated astronomers, they've also left their mark on pop culture, inspiring everything from gripping sci-fi novels to blockbuster films. Take the movie Interstellar, for example. While it doesn't directly feature dark stars as we know them, the film's portrayal of a black hole named Gargantua borrows some of the same eerie, otherworldly allure. The swirling vortex of light and distortion around Gargantua captures the same sense of awe that dark stars might evoke, cosmic giants lurking in the shadows of the universe, warping space and time. It's a playful nod to how real-world astrophysics can spark creative visions, even if Hollywood takes a few artistic liberties. Then there's literature. Sci-fi authors have long toyed with the idea of stars powered by exotic energy sources, much like dark stars. In Alastair Reynolds' Revelation space series, for instance, ancient alien artifacts hint at stars sustained by something far stranger than fusion, echoing the dark matter annihilation that fuels theoretical dark stars. These stories blend real science with speculation, offering a tantalizing glimpse of what might be lurking in the cosmos. Even video games have joined in. Titles like Mass Effect and No Man's Sky feature celestial phenomena inspired by real astrophysical mysteries, including dark stars. Players can explore rogue planets orbiting dead stars or encounter bizarre energy signatures, each one a playful reinterpretation of the science behind these elusive objects. What's fascinating is how often pop culture gets eerily close to the truth. Dark stars challenge our understanding of how the universe works, and that sense of mystery resonates with storytellers. Whether it's a novel about ancient cosmic entities or a film exploring the edges of space-time, dark stars serve as a reminder that reality can be just as strange as fiction. So the next time you watch a sci-fi epic or lose yourself in a cosmic adventure, keep an eye out for those subtle nods to real science. Who knows, the next great portrayal of a dark star might be lurking in plain sight, waiting to inspire both scientists and dreamers alike. Coming up, we'll tackle some of the biggest misconceptions about dark stars, because even the most mysterious objects in the universe have their share of myths that need debunking. Now let's clear up some confusion. Dark stars are shrouded in mystery, and that mystery has led to plenty of misunderstandings, one of the biggest myths. That dark stars are just another name for black holes. While both are cosmic heavyweights, they're fundamentally different beasts. Dark stars, if they exist, would be massive structures powered by dark matter annihilation, not by the gravitational collapse that creates black holes. Imagine a star so large it could dwarf our entire solar system, yet instead of burning through nuclear fusion like the Sun, it glows faintly from the energy released as dark matter particles collide and annihilate within it. That's a dark star. Black holes, on the other hand, are regions of space-time where gravity is so intense that nothing, not even light, can escape. No glow, no annihilation, just an invisible point of no return. Another common mix-up is the idea that dark stars are failed stars or dead remnants. That's not the case either. Theorized to form in the early universe, dark stars would have been luminous giants in their own right, radiating heat and light, just through a completely different process than modern stars. They wouldn't fade into darkness like burned-out embers. Instead, their lifespan would depend on the availability of dark matter fuel. Run out of that, and they'd collapse, possibly seeding the supermassive black holes we see at the centers of galaxies today. Some folks also assume dark stars must be invisible because of the word dark in their name. But here's the twist: they'd actually emit visible light, albeit faintly. Their glow would come from the heated ordinary matter within them, even if the primary energy source is invisible dark matter. Think of it like a lantern with a dim bulb. The light is real, but the power behind it is hidden. Then there's the myth that dark stars are purely science fiction. While they haven't been observed yet, their existence is grounded in real physics. Theories involving dark matter's behavior and early universe conditions make them a compelling possibility, one that telescopes like the James Webb Space Telescope are actively hunting for. So why does this all matter? Because misconceptions can muddy the waters of discovery. If we dismiss dark stars as just another black hole or a sci-fi trope, we might miss the chance to uncover one of the universe's oldest secrets. The next time you hear about these cosmic enigmas, remember, they're not holes, they're not failures, and they're definitely not fiction. They're a window into a universe far stranger and more wonderful than we've ever imagined. Up next, we'll explore how the hunt for dark stars is bridging gaps across science, from particle physics to philosophy. Because sometimes the biggest discoveries start by asking the right questions. One fascinating aspect of dark stars isn't just what they could tell us about the cosmos, it's how their study ripples across entirely different fields of science and thought. This isn't just an astronomy puzzle, it's a crossroads where particle physics, cosmology, and even philosophy collide. Take particle physics first. Dark stars, if confirmed, would be direct evidence of dark matter's behavior in extreme environments. Right now, dark matter particles are hypothetical. We infer their existence from gravitational effects, but we've never caught them in the act. Dark stars would change that. Their theorized power source, dark matter annihilation, would offer a cosmic laboratory to study how these elusive particles interact, decay, or even transform. It's like finding a hidden instruction manual for the universe's most mysterious ingredient. Then there's cosmology. Dark stars could rewrite the story of how structures formed in the early universe. Picture this: if these giants existed, their sheer mass and energy might have accelerated the growth of galaxies, bending space and time in ways we haven't accounted for. Their potential collapse into supermassive black holes could also solve a lingering mystery: how galactic cores grew so massive so quickly after the Big Bang. Suddenly, dark stars aren't just oddball objects, they're potential missing links in cosmic evolution. But the surprises don't stop there. Philosophers are drawn to dark stars for what they represent, a reminder of how much we still don't know. Could the universe's first light have come from an entirely different kind of star? If so, what does that say about our place in the cosmos? As one philosopher put it, dark stars challenge the very framework we use to define normal in the universe. They force us to question whether our assumptions are limits or just blind spots. Even technologists are paying attention. The hunt for dark stars pushes telescope engineering to its limits. Instruments like the James Webb Space Telescope aren't just built for known targets, they're designed to uncover the unexpected. Every upgrade in sensitivity or resolution brings us closer to spotting these ghosts of the early universe or ruling them out entirely. So why does this interdisciplinary dance matter? Because breakthroughs rarely happen in isolation. A discovery about dark stars could send shockwaves through multiple fields, reshaping textbooks from physics to philosophy. And that's the beauty of science. The bigger the mystery, the wider its reach. Up next, we'll tackle the ethical questions surrounding this search, like whether chasing cosmic ghosts is worth the investment when Earth faces its own urgent challenges. Sometimes the stars force us to look inward as much as outward. Now let's shift our gaze from the cosmos to our own backyard, because the hunt for dark stars isn't just a scientific challenge, it's an ethical dilemma too. In a world grappling with climate change, poverty, and pandemics, should we really be spending millions chasing hypothetical stars from 13 billion years ago? It's a fair question, and one that deserves honest exploration. On one side of this debate are the pragmatists. They argue that every dollar spent peering into the early universe is a dollar not spent solving immediate Earth-bound problems. Telescopes like the James Webb Space Telescope cost billions to build and operate, money that could fund renewable energy projects, medical research, or education initiatives with clear, measurable impacts on human lives. When families struggle to put food on the table, does it really matter whether the first stars ran on dark matter? The counter-argument is blunt. Pure science is a luxury we can't always afford. But then there's the other perspective, one that sees fundamental research as an investment in humanity's future. Every major technological leap in history, from GPS to medical imaging, traces back to impractical discoveries about how the universe works. Dark stars might seem irrelevant today, but understanding them could unlock new physics with unforeseen applications. Dark matter research alone has already spurred advances in detector technology that's now used in medicine and security systems. Who's to say what spin-off technologies might emerge from this cosmic detective work? There's also the intangible value of inspiration. Space exploration has always been humanity's grandest classroom, sparking generations of scientists, engineers, and dreamers. The simple act of searching expands what we believe is possible. As one astronomer put it, we don't just explore space to find answers, we do it to remind ourselves what questions we should be asking. In an era of short attention spans and immediate gratification, dark stars represent the ultimate long game, knowledge for its own sake, pursued simply because it's there. The debate gets even more nuanced when we consider opportunity costs. Building the next generation of space telescopes doesn't happen in a vacuum. It requires cutting-edge materials, computing power, and engineering that often benefits other sectors too. The technologies developed to study the early universe frequently find uses in climate monitoring, disaster prediction, and communications. So perhaps the choice isn't between studying stars or solving Earth's problems, but about how to do both in ways that amplify each other. Ultimately, this isn't just about dark stars, it's about what kind of civilization we want to be. Do we focus solely on survival, or do we also nurture curiosity? History suggests civilizations thrive when they balance both. The Egyptians built pyramids while perfecting agriculture. The Renaissance merged art and science. Maybe the lesson is that humanity's greatest achievements come when we refuse to choose between practical needs and cosmic dreams. As we continue pushing the boundaries of knowledge, these ethical questions won't disappear. But perhaps they shouldn't, because wrestling with them keeps our priorities in check, ensuring that whether we're studying the birth of stars or the future of our planet, we never lose sight of why we explore in the first place. Next, we'll step into a fascinating thought experiment. What if dark stars weren't just ancient history? What if they still existed somewhere out there? Time to stretch our imaginations beyond the observable universe. Let's take a moment to dream a little. Picture this: a universe where dark stars didn't vanish billions of years ago but still linger in the cosmos today. What would that look like from our tiny corner of existence? Close your eyes and imagine stepping outside on a clear night, only instead of the familiar twinkling points of light, the sky is dotted with something far stranger. These wouldn't be the stars we know. Dark stars, remember, don't shine from nuclear fusion. They glow faintly from dark matter annihilation, a process so alien it would paint the heavens in ways we've never seen. Imagine colossal, shadowy spheres, each 100s of times wider than our solar system, radiating a deep, eerie light, more like the dim embers of a dying fire than the sharp, bright pins of modern stars. The night sky might feel softer, even haunting, with these primordial giants casting a ghostly haze across constellations. And here's where it gets trippy. Because dark stars could grow so massive, they'd warp space-time around them more intensely than any star today. Their gravity might bend the light of galaxies behind them, creating natural cosmic lenses that distort the sky into surreal, funhouse mirror vistas. Imagine looking up and seeing entire galaxies stretched into shimmering arcs around these dark behemoths, a sight no telescope has ever captured. Now think about scale. If a single dark star replaced our Sun, its surface could extend beyond Jupiter's orbit. From Earth, it wouldn't appear as a distant dot but as a vast, looming presence, swallowing half the sky in a dull, otherworldly glow. Seasons as we know them would vanish, bathed in perpetual twilight. Life under such a star, that's a puzzle for another day, but it's fun to wonder. This isn't just fantasy, though. If dark stars do still exist hidden in the universe's deepest corners, they'd challenge everything we know about stellar evolution and cosmic history. Could they be lurking in plain sight, masquerading as supermassive black holes or strange, dim galaxies? That's what makes this thought experiment so thrilling. It forces us to question the limits of our cosmic map. So now it's your turn. Drop your wildest ideas in the comments. How would you describe a night sky ruled by dark stars? Would their eerie glow inspire awe or unease? Could life exist in their shadow? And if you stumbled upon one, what would you name it? Let's turn this into a brainstorming session, because sometimes the best science starts with a simple what if. Up next, we'll dive into cutting-edge research that might settle this debate for good. A recent study claims to have found indirect evidence of dark stars. But is it the breakthrough we've been waiting for, or another cosmic false alarm? Let's weigh the facts. Now, let's turn from imagination to investigation. In 2023, a team led by astrophysicist Katherine Freese published a paper that sent ripples through the scientific community. Their claim: they might have found the first indirect evidence of dark stars hidden within data from the James Webb Space Telescope. This isn't just another theoretical exercise. It's a potential game-changer that could rewrite our understanding of the early universe. Freese and her colleagues focused on 3 unusually bright objects spotted in JWST deep field images. These cosmic anomalies, dating back to when the universe was less than 500 million years old, glowed with characteristics that didn't quite match normal young galaxies or quasars. The team's breakthrough came when they modeled these objects' light signatures. Traditional stars couldn't explain the observed infrared spectra, but dark stars fueled by dark matter annihilation fit the data remarkably well. Think of it like hearing a strange melody in space and realizing only one exotic instrument could produce those exact notes. The methodology hinged on painstaking spectroscopic analysis. By breaking down the light from these objects into its component wavelengths, researchers could hunt for telltale gaps or spikes that reveal an object's composition and energy source. Dark stars, unlike fusion-powered stars, would show distinct absorption features tied to their dark matter engine. Freese's team argued that these fingerprints matched their models of supermassive dark stars, some potentially weighing in at over 1 million times the mass of our Sun. It's cosmic detective work at its finest, where every photon tells part of the story. But as with any bold claim, skepticism followed. Critics point out that alternative explanations exist. Could these objects instead be dense clusters of population 3 stars? The universe's first normal stars made purely of hydrogen and helium, or perhaps they're early galaxies with unexpectedly intense star formation. The debate centers on whether the data conclusively rules out these more conventional possibilities. Some astronomers argue we're seeing a cosmic Rorschach test, where researchers predisposed to dark star theories might be interpreting ambiguous data through that lens. The stakes are high because confirmation would revolutionize astrophysics. If even one of these candidates is a bona fide dark star, it would prove that dark matter can indeed form stable, luminous structures, something never before observed. It would also offer clues about how supermassive black holes grew so quickly in the early universe, potentially solving 2 cosmic mysteries with one discovery. But extraordinary claims require extraordinary evidence, and the scientific process demands rigorous peer review before any paradigm shifts occur. What makes this case study fascinating is how it embodies the spirit of exploration. Whether Freese's team ultimately proves correct or not, their work pushes boundaries by asking daring questions. It challenges us to consider not just what we know about the cosmos, but how we know it. And that's the essence of good science, venturing into the unknown, one careful observation at a time. As we wait for further observations to settle the debate, one thing is clear: the hunt for dark stars has entered an exciting new phase. Up next, we'll zoom out to see how this search connects to bigger questions about the universe's infancy. and why dark stars might hold keys to understanding everything from galaxy formation to the nature of dark matter itself. Now, as we bring our cosmic journey to a close, let's take a moment to reflect on the puzzle of dark stars, these ghostly giants that may have lit up the infant universe. Their very existence challenges everything we thought we knew about how stars form and evolve. Imagine uncovering a hidden chapter of cosmic history, one where dark matter wasn't just an invisible scaffold but the fuel for colossal, glowing behemoths. That's the scale of what's at stake here. If dark stars are real, their discovery wouldn't just be another footnote in astrophysics, it would rewrite entire textbooks. Picture this, a star so massive it defies conventional physics, powered not by nuclear fusion but by the annihilation of dark matter. Such a finding would bridge two of science's greatest mysteries, dark matter and the formation of the first cosmic structures, in ways we're only beginning to grasp. It could explain how supermassive black holes appeared so early in the universe's timeline, solving a riddle that's puzzled astronomers for decades. Yet the hunt is far from over. The James Webb Space Telescope, our most powerful window into the distant past, is just getting started. Every new image it captures, every spectrum it analyzes, brings us closer to answering whether these enigmatic objects are out there. Think of it like tuning a radio to the static of the cosmos, searching for that faint but unmistakable signal of a dark star's whisper. The process is slow, meticulous, and utterly thrilling. What's remarkable is how this quest embodies the spirit of science itself, embracing uncertainty, testing bold ideas, and staying open to surprises. Whether dark stars are confirmed or debunked, the search alone pushes our understanding forward. It reminds us that the universe is full of surprises, and sometimes the most revolutionary discoveries come from questioning what we think we know. So, where do we go from here? Keep watching the skies and the headlines. Follow the James Webb's ongoing missions, because the next big breakthrough could be just one observation away. And stay curious. After all, the greatest cosmic mysteries aren't just for scientists to solve. They're for all of us to wonder about. Who knows, the next time you gaze up at the night sky, you might just be looking at the answer hidden in plain sight. If you've enjoyed unraveling this cosmic enigma with us, don't forget to hit like and subscribe for more deep dives into the universe's biggest questions. Drop a comment below. Do you think dark stars are out there waiting to be found? Let's keep the conversation and the hunt alive. As we wrap up this cosmic adventure, let's take the excitement beyond this video. The story of dark stars isn't just for astronomers, it's a puzzle we can all explore together. If this journey through the universe's hidden past sparked your curiosity, don't let it end here. Hit that like button to let us know you enjoyed the ride, and subscribe so you won't miss our next deep dive into the cosmos. The universe is full of mysteries waiting to be uncovered, and we're just getting started. Now we want to hear from you. Do you think dark stars are lurking in the ancient corners of space, or could there be another explanation for those strange, glowing giants the James Webb Telescope might be spotting? Drop your thoughts in the comments below. Let's get the debate going. Whether you're team dark star or team wait and see, your perspective adds to the conversation. And here's something to keep your eyes on: the stars. The James Webb Space Telescope is far from done. Its next big discovery could be just around the corner, and we'll be here to break it down for you. What if the next image it beams back holds the key to unlocking this cosmic mystery? Make sure you're subscribed and have those notifications turned on, because you won't want to miss it. Until then, keep looking up. The universe is vast, strange, and full of surprises, and who knows, the answer to the dark star riddle might be closer than we think. Thanks for joining us on this journey, and remember, the greatest discoveries often begin with a simple question. So stay curious, stay wondering, and let's keep exploring the unknown together. See you in the next video.